Iowa, the heart of the nation's agricultural belt, and home to the world's richest farmland, ripe with corn and soybean fields. As a leading agricultural center, Iowa draws people from around the globe seeking the latest advancements in farming. However, with the recent completion of the environmentally sensitive Iowa River Bridge, the state is also drawing attention for its innovative bridge design and construction that not only preserved the Iowa Greenbelt, but brought about the long-anticipated completion of US 20 from Dubuque to Fort Dodge. The original US 20, constructed in the 1920s, was a narrow, meandering road that was designed for less traffic and slower speeds. Then in the 1960s, the Iowa Department of Transportation began modernizing the old road, replacing it with a 4-lane highway. But it was never able to fully complete the route for financial and environmental reasons. As a result, portions of US 20 in Hardin and Grundy counties remained unfinished for nearly 30 years, forcing motorists to drive through many small towns, slowing the flow of traffic and inhibiting economic growth.
It got to the place where the Iowa River Greenbelt area on the Iowa River was obvious it was going to be a kind of a problem area for us to work through because of a lot of environmental concerns by citizens who thought the Iowa River Greenbelt was something that was very special and very unique, and it was. It was also equally obvious that we had to get through there. And so the question became, how do you do it? And these things take a lot of time to work through because there are so many issues to deal with, so many people that have strongly held beliefs on each side.
Today, US 20 is a continuous 4-lane highway from Dubuque, a city on the state's eastern border, to Fort Dodge, 200 miles to the west. With the completion of the most recent 27-mile section, motorists will save an estimated 16 minutes of travel time. The improvements to this corridor have the potential to positively impact the economies of communities located along the route.
So modern 4-lane or multi-lane, safe, convenient highways are good for everybody. They're good for the state. They're good for the local communities that will attract businesses. They're good for motorists. It's a win-win-win all the way around.
The long delay in completing US 20 was primarily centered on the many complex environmental issues associated with the project. To complete US 20, a bridge had to be built over the Iowa River, which runs through the Iowa Greenbelt in Hardin County. The Greenbelt is a 50-mile-long, environmentally protected natural oasis that parallels the Iowa River, a rare natural treasure filled with old-growth timber, endangered and threatened plant and animal species, and historical archaeological remnants. Because the Greenbelt is such a unique and cherished link with nature and the past, lengthy environmental studies were required by the federal government before construction of the Iowa River Bridge could begin. These studies began in 1968 and weren't fully completed until 1996, when the final site for the bridge crossing was chosen.
It just makes a lot of sense that we need to coexist with our environment in a friendly way and do things in the best possible way that serves not only the traveling public, but also protects and limits damage to the environment.
Several highway alignments were studied before the final route was chosen near the town of Steamboat Rock. The chosen bridge site offered a number of advantages over other locations, primarily that it only affected about 10 acres of the Greenbelt and provided more suitable soil conditions for constructing the bridge. Other potential sites may have had fewer environmental and archaeological issues. However, the soil conditions at these sites were not conducive for bridge construction. The environmental studies at the final bridge site revealed several issues that the Iowa Department of Transportation would have to address before, during, and after construction, including bald eagle roosting sites, rare freshwater mussel species inhabiting the Iowa River, an endangered species of monkshood plant, noise intrusion from the bridge traffic into the wooded areas, and a number of ancient Native American campsites. Designing and building a bridge while addressing the strict environmental concerns surrounding the Greenbelt would ultimately determine the success of the project. Led by the Iowa Department of Transportation, a team was formed for the design of the bridge. The team included the Federal Highway Administration and the HNTB Corporation, a bridge design consulting firm. HNTB developed several bridge design alternatives and evaluated each for cost, construction feasibility, and minimal visual impact to the Greenbelt. The findings were presented to the Iowa DOT for consideration.
When we were first contracted by the Iowa DOT, we originally thought we would span the river with a longer span structure. But when we saw the aesthetic criteria, we soon realized we had some challenges ahead of us. One of them being that the bridge could not overpower the environment of the river valley. So we looked at some deck trusses, we looked at an under-the-deck arch, we looked at some segmentally constructed concrete structures, and then of course the ultimate suggestion was the launched four-girder system, which we pursued into further design for the DOT.
A 5-span steel I-girder bridge was HNTB's recommended design, and the Iowa Department of Transportation agreed for several reasons. The I-girder bridge could be erected using a method called incremental launching, which would minimize the need for heavy construction equipment in the river valley, thus minimizing disruption to the environment. Secondly, the superstructure of the bridge has a very slender profile with minimal visual impact on the Greenbelt, a design feature that the Iowa DOT required.
We looked at the different types, and the decision was made to go with the steel I-girder, mainly because it was a low-profile bridge, and with the weathering steel, we thought that that fit into the natural environment better than the other types.
Third, the 5-span bridge design required the fewest number of piers, reducing construction activity in the river valley. And finally, the girders used were fabricated from weathering steel.
There are several reasons why we chose to use weathering steel. One reason, because it is cheaper than painted steel. You don't have to worry about painting the structure initially, or you don't have to worry about repainting the structure every 20 years or so. That require full containment to remove the paint and repaint it. The uniform brown color it develops over time does not fade like painted steel. It does have better corrosion properties.
The bridge is 1,630 feet long, with separate deck structures for the east and westbound lanes. Each deck structure has 5 302-foot steel girder spans and 2 60-foot pre-stressed concrete end spans. The steel girder spans are supported by 4 tall concrete piers and 2 shorter end piers, none of which are located in the Iowa River.
There are 4 really tall piers, we'll call them tall 2-column piers. They're up to about 120 feet above the ground, and the cap beam, the upper part that supports the girders, is about 86 feet wide. They were constructed, 2 of them on driven steel piles, H-piles that were driven into the ground 90 to 100 feet. Each one of those piers is actually supported by 72 of those steel piles. The 2 piers right adjacent to the river, piers 3 and 4, are supported on 8-foot diameter drilled shaft foundations that are about between 95 and 100 feet long down into the limestone bedrock. The reason the drilled shaft foundations were selected for those piers was the fact that they allowed the pier footings, the part that's buried in the ground, to be much smaller in dimension, so they didn't intrude into the Iowa River.
The outer piers are located on the slopes of the river valley. They are supported by steel H-piles driven to 100-ton bearing capacity. The steep slope of the river valley required the contractor to stabilize the soil around the piers and abutments with permanent slope protection. The Iowa River Bridge was the first to utilize the incremental launching method of construction for a steel I-girder bridge of this size.
Well, for the Iowa River Bridge project, we were looking at a 4 I-girder steel system, which really had not been done at that time. The launching system, or the theory, is used widely in Europe, but primarily for a concrete box system. When we suggested the launching of a 4 girder system to the Iowa DOT, they asked us to pursue that a little further.
The project plans were prepared by HNTB and included a suggested launching erection sequence. Jensen Construction, with assistance from Ashton Engineering of Davenport, then developed a detailed erection sequence very similar to HNTB's and designed the complete launching system. The entire launching system was thoroughly reviewed by HNTB and approved by the Iowa DOT. Independent computer models were developed and compared to ensure that no detail was left unchecked. The incremental launching method of construction required the bridge superstructure be assembled on temporary supports behind one abutment and launched or rolled longitudinally. Additional girder sections were then added to the rear of the train as needed. The process was repeated until the leading end of the bridge landed on the opposite side of the river.
Once the launching nose and the tail section were attached, then the girders were launched one span forward. So the nose was landing on the first pier at that point. Once that first launch was complete, the tail section is removed from the back of the bridge and additional steel girder sections are added on the back. And the same process is continued time after time.
A launching pit was excavated above the slope of the East River bank and served as a staging area for the I-girder assembly. The pit was excavated beneath the future approach roadway to limit any unnecessary construction disturbance of the natural surroundings. The pit was approximately 600 feet long, 125 feet wide, and 15 feet deep. The length of the pit was necessary to assemble a sufficient length of girder train to provide sufficient counterbalance for the unsupported or cantilevered end of the first span as it was being launched. A series of 7 falsework piers were constructed in the launching pit to support the girders and rollers during steel erection and launching. Each roadway superstructure consists of 4 11-foot 4-inch deep I-girders on 12-foot centers. The flanges of the girders are up to 30 inches wide and 3 inches thick. The girders were fabricated in sections as long as 95 feet and weighing as much as 90,000 pounds. The middle 2 girder lines were reinforced with heavy lateral bracing for both the top and bottom flange. This bracing provided the critical torsional support needed to prevent the spans from twisting or racking as they were being launched.
If you think of a box, it gains its torsional resistance, or its resistance to a twist, based on the proportions of that box. Now, if you compare that with a girder that's the shape of an eye, there's not much resistance to that twist. But if you actually link 2 of them together with bracing top and bottom, you could sort of form a box. And that's basically what we did on the Iowa River Bridge. We took the center 2 girders, linked them with bracing on the top and bottom, and formed sort of a spine for the entire launch.
A tapered launching nose was temporarily attached to the front end of the leading girder span. The launching nose was a 146-foot tapered girder weighing 150,000 pounds. The launching nose served 2 primary purposes. The tapered section reduced the weight of the cantilever span, but more importantly accounted for the vertical deflection of the cantilever span.
As the launching span approached the pier it was headed towards, that cantilevered section obviously would deflect downward, and hopefully the deflection was not any greater than the difference in the launching nose, so that when the launching nose got to the pier we were headed towards, it landed above the rollers on that pier, and as we proceeded with the launch, we were able to push the cantilevered span back up to its needed elevation.
One of the unique features of a launched girder system is the use of a launching nose. Its primary purpose is to lighten the cantilevered portion of the bridge that's being pushed from pier to pier. When we originally calculated the initial deflections on the girders, nobody believed us when we predicted about a 7.5-foot deflection on the nose. It was an amazing sight when we were actually on the job site and that nose actually dropped down 7.5 feet just as we predicted.
Without the nose, the cantilevered end of the girder span would hit the side of the pier instead of gently landing on top. The end of the girder train was equipped with a tapered launching tail. The tapered tail prevented the end of the girders from abruptly dropping off the rollers.
The tail also carried the big whaler beam that the post-tensioning bars were connected to, which helped to distribute the load to the girders in a little more uniform fashion. And that was a pretty critical part of the launch as well.
After each launch was completed, the tail section was removed, the next group of steel girder sections installed, and the tail reinstalled prior to making the next launch. The hydraulic ram jacking system provided the necessary horizontal force to launch the bridge across the river. It was powered by two 250-ton hydraulic rams, one located on each side of the girder spans.
The hydraulic rams were mounted to a large platform that was welded to several piling that were driven in the ground. 3 or 4 of those piling on each side of the bridge were driven with a batter to help resist the horizontal forces that were going to be imposed on them by the pulling force that was reacting on the bridge.
The jacks actually pulled the launch forward, but the launch was being pushed. If you could imagine the jacks at the front of the launching pit connected to a transfer beam at the back of the launch with the use of some tension rods. The jacks actually pulled forward, but due to the mechanism of the transfer beam actually pushed the launch forward.
The high-strength thread bars were joined with couplers in 15-foot-long sections. The launching operation was run continuously for a 15-foot increment. At that point, the launching was stopped temporarily while one section of thread bar was removed from each side, the couplers were reconnected, and launching resumed. Each 15-foot launching cycle lasted 20 to 23 minutes, including time to remove and recouple the thread bars.
The post-tensioning bars are virtually just a large diameter bar. They're about 2 3/4 inches in diameter, have very high tensile capacity, which was needed because we wanted to have a little safety cushion on how much load we could put in the post-tensioning bars. We could have actually went down to the 1.5 inch diameter range, but that was going to put us real close to the ultimate strength of the bars. We want a little safety cushion there. We basically were shooting for somewhere around 150 ton to 200 ton of capacity in the post-tensioning bars.
At this distance, it was difficult to see the girders moving at a rate of 1 foot per minute. But by speeding up the footage 12 times normal, it makes the movement of the girders much easier to see. And if someone was too far away to see if the girders were actually moving, all they had to do is listen. The noise given off by tons of eye girders being pushed over heavy-duty steel rollers was unmistakable. 2 independent sets of heavy-duty rollers were used to support and guide the girders during launching. 18-inch diameter vertical rollers were used to support the weight of the girders at the falsework piers in the launching pit and on each of the concrete piers. 1 vertical roller was placed under each girder line on each pier.
The load rollers, which facilitated the longitudinal travel of the bridge itself, were, I believe, 18 inches in diameter, made out of hardened 6-inch thick steel. They had a steel axle in them. The bridge traveled roughly 1 foot a minute while we were during the launch. With the 18-inch diameter wheels, was less than 1/5 of a revolution per minute.
A separate set of horizontal guide rollers provided steering control and kept the girders in line and on center during launching.
On every pier, we had 2 of these rollers. They were about an 8-inch roller. They were each supported with a 100-ton ram that allowed us to put a horizontal force of 100 tons on the bridge as it went past each pier. We also had those guide rollers in the launch pit to help steer the bridge in the launching pit and keep control of it.
A set of transition ramp plates were installed at the lead and tail end of the steel girders where they were bolted together. This was done so that the rollers could accommodate the thickness change of the bottom flange. After the first span reached the second pier, the launching was stopped. The next span of steel girders were then assembled in the launching pit and bolted to the rear of the first span. This process continued until all 5 spans of the eastbound bridge had been launched. The launching nose was removed and returned to the east side of the river where it could be reused for the launching of the westbound bridge. Researchers from Iowa State University were hired to observe the bridge during launch events.
We installed several different types of sensors on various locations of the bridge. These included strain sensors, strain gauges, tilt meters, as well as some deflection instrumentation. And we looked at critical locations on both the superstructure as well as on the substructure to try and relate 2 things. To first determine if there was any damage that occurred during the construction, and second, to try and quantify and validate some of the assumptions that may have been made during the original design.
When the launching process was completed for each bridge structure, the steel girders were jacked up and the rollers removed. Permanent pot bearings, which distribute the weight of the girders to the piers, were then installed, and the girders were lowered onto the bearings. The bridge contains a unique sealed stormwater and runoff collection system. This system collects all stormwater and melting snow, which carries road salt, sand, and debris, from the deck of the bridge and channels it to a storage basin near the west abutment.
The lay of the land kind of brings the water towards the river, so they had to figure out a system to keep that water from directly running into the river, because during the winter, salt runoff and that, they didn't want to directly go into the river. So there was a drainage system established on each side of the river that would collect the water and bring it to a holding pond, and that would allow the salt in that to settle out.
When launching was completed in March of 2002, nearly 10 million pounds of steel had been launched nearly a quarter of a mile across the Iowa River Valley. At the time of construction, this bridge was the longest launched steel I-girder bridge in the world. With the steel girder spans in place, the concrete decks of the bridge were ready for construction. The roadway decks rise approximately 137 feet above the Iowa River and consist of 2 separate structures, one for the eastbound and one for the westbound lanes. Each structure provides a 39-foot wide roadway with concrete barrier walls along both sides. The exterior barrier walls are equipped with an open steel railing that will permit the traveling public to admire the Iowa River Valley as they cross the bridge. The bridge decks consist of an 8.5-inch thick high-performance concrete deck with a 1.5-inch high-density concrete wearing surface. This wearing surface is intended to protect the reinforcing steel in the deck and provide a much longer life. It can be removed and replaced in 20 to 30 years if needed. Strict environmental guidelines were enforced to protect and preserve the Iowa Greenbelt throughout the entire project. Working within these guidelines would constantly test the bridge team's ability to adapt and solve problems. All construction activity in the river valley was limited to areas identified in the contract plans.
The main challenge we had down in the river valley mainly was the amount of room that we had. The drill shaft operation did require a fair amount of equipment and support equipment.
All heavy construction equipment in the river valley was required to have a containment system to prevent accidental fuel or hydraulic fluid spills from reaching the river. In addition, fuel and chemical storage was not permitted within the defined environmentally sensitive work zone. The contract provisions presented the possibility of a winter shutdown if the construction activity was believed to be adversely affecting the winter roosting habits of the bald eagles in the area.
Eagles are typically pretty wary of human contact. So the Fish and Wildlife Service people with the Fish and Wildlife Service as well as the Iowa DNR felt that if we were in there making noise during these winter months, that they might abandon the Iowa River Greenbelt and have to seek refuge elsewhere.
On-site biological monitoring showed that the bald eagles were not disturbed by the construction, and work was allowed to proceed. Aggressive erosion prevention measures were an important part of the project. The first activities at the site were the installation of silt fences. A weekly inspection of all erosion control measures was performed by biological monitors from the Iowa DOT. Underground artesian water on both sides of the river required the contractor to take several extra precautions to protect the Iowa River from contamination during the pier shaft drillings.
What artesian water is basically water that's trapped in the ground under pressure. And if you drill into a pocket of artesian water, it will actually work its way up through the drill hole and make its way to the surface. The problem is it's too clean and too cold for the mussels in the river to be able to tolerate. So all the artesian water on the site had to be contained and not allowed to get into the river. The piers right adjacent to the river, piers 3 and 4, were constructed inside of a cofferdam. In addition, there was 2 steel casings that surrounded the drilled shaft foundation. Those again were higher or taller than the pressure of the artesian water would allow it to reach.
The contract plans prohibited the use of causeways and temporary bridges to cross the river. Although the river is only 275 feet wide at the bridge site, the contractor was required to drive almost 10 miles around to the nearest small county bridge in order to access the other side of the river. In addition, a biologist was on site during construction to monitor any negative effect the construction was having on the river and the rare species of freshwater mussels. Monthly water quality samples were taken at the site and downstream to ensure that no leakage from the site was allowed to enter the river.
There were 16 different species of mussels found along a 17-mile stretch of the river. Of those 16 species, 3 were listed on the Iowa State Threatened Endangered Species list. They were the strange floater, which is state threatened, the elk toe, which is state threatened, and the fluted shell, which is a state endangered.
The construction crew not only had to protect the environment from the construction activities of building this bridge, they had to protect themselves against the harsh reality of an Iowa winter.
Probably the biggest problem of the weather was in the first winter the winter of 2000-2001. We had a very severe winter and a lot of snow. We were working on foundations during that period, and it slowed things down. Work never really quit for more than a couple days at a time due to weather. There were some pretty cold days out there and a lot of snow, but people kept working away.
After bridge construction was completed in November 2002, all disturbed areas were restored to their near pre-construction condition. This included reseeding and replanting as needed, and removing and restoring any minimal access paths that were constructed into the valley. The protection of the Greenbelt hasn't ended with the completion of the bridge. Regular environmental monitoring will continue for the next 3 to 5 years to alert officials to any adverse environmental impacts occurring within the Greenbelt. In recognition of these environmental efforts, Mary Peters, the Federal Highway Administrator, presented the Iowa DOT with the Administrator's Environmental Quality Award during a ceremony held at the bridge in September 2002.
Iowans have a long history of innovative approaches in highway transportation, and this US 20 project is a fine example of the ingenuity and the tenacity that it takes to provide needed mobility while respecting environmental treasures.
After nearly 30 years of environmental and alignment studies, 2 years of design, and 28 months of construction, the Iowa River Bridge was opened to traffic on August 22, 2003, following a public ribbon-cutting ceremony. As testament to the bridge teams and highway construction crews' accomplishments, the opening was attended by hundreds of Iowans, Federal Highway Administration Associate Administrator Charles Nottingham, Iowa Department of Transportation Director Mark Wondrove, members of Iowa's congressional delegation, many local officials, and representatives of the US 20 Corridor Association and Governor Tom Vilsack.
when a road like this is constructed that there are a lot of interests that need to be balanced. And the innovative techniques that have been used in the construction of this segment to not only provide economic opportunity but also to protect the environment speak to a great deal about the acceptance of our responsibility to preserve our natural resources and to enhance those natural resources.
The Iowa River Bridge required innovative solutions to a series of complex problems. With complicated environmental issues literally surrounding the project, the Iowa Department of Transportation and its design and construction partners, together with the citizens of Iowa, designed and built an environmentally friendly bridge that politely navigates the Iowa Greenbelt while vastly upgrading the transportation infrastructure of the state.